Yeah. I just want to make sure. Yeah. I just think time limit is just fine. I didn't give up. I used to say that I didn't say that.
Okay, Sarah B. Claire. Matt. Luke. Oh, you're Matt? Matt Campbell? Okay, yeah, cool. Luke. Yeah, okay, yeah. Jaden. Emma. Right. And Eliza, yes. Stuart. Yep. Ethan. Manya. Olivia. Kushal. Diego. Darwin. Yeah. Sean. Jules. Yeah. Doa. Matthew. Right. Colin. Yeah. Emily. Yeah. Rennick. Sarah T. McKenna. Okay, and yeah, name? Olivia. Rennick. Name, please. Sorry? Claire. Yes, gotcha. Okay, did Sarah B come in? Yeah, there she is. Okay. And Kushal. No? Okay. Okie dokie. Okay, sorry for the late start. So here we go. What we were talking about last time. Let's see. Oh gosh, let me check my notes here. We were 2 pages in it. Yeah, okay, right. Okay, exactly. Okay, so we talked about parametric curves and parametric derivatives, right? Derivatives are velocities. Anti-derivatives give you a plus C, right? You evaluate the integration constant in the usual way by, plugging in t equals 0 and solving as needed. A lot of that's extremely familiar from single variable calculus. Okay, all right, so moving along. Okay, so arc length. If you have a parametric curve, you could reasonably ask, how long is it? Between a certain starting point and a certain ending point. And there's a little bit of machinery that's nice to build up in order to answer that question. And this is machinery that's going to be useful elsewhere as well. We'll start off with, given this parametric curve, let's talk about the tangent vector. This is called the unit tangent vector, and it's literally just a unit vector pointing in the direction the curve is going. Easy formula, of course. We know that the derivative, being the velocity vector, is a tangent vector. So if you want the unit tangent vector, you just normalize, namely you just divide by the magnitude. Okay, so no big deal there. Now, next thing we want to talk about is the dx vector, what I like to call the position differential. I say position differential because, well, it's x is the position, and we're talking about the differential of position, right? So in other words, you're asking, in a given little small amount of time dt, what is our linear estimate in the change of position? Now, the actual change in position is that we were there and we became there because the curve did, as curves do, curve, right? But based on what's going on at at this point, and just looking at the velocity at that moment, our estimate of how much the position would change is not going to be quite the same. It'll be off by a little. It won't account for the curving. Right? Okay. So the formula. Oh yeah, question.
Yeah. So underneath where it says unit vector in this direction,
Uh-huh.
is there a prime next to the x?
Yeah, because so this x prime is the velocity. It's velocity of the parent. Yeah. So the idea is that velocity is a tangent vector, and then if you want the unit, then you divide by the magnitude. Yeah. Okay. So yeah. So dx again, just based on what's going on at that particular point, at that particular instance, your best estimate of your change in position is velocity times time, right? It's an old formula from physics. Change in position is velocity times time. You could think of that as kind of the definition of velocity, arguably. Okay. All right, so you write that down. Don't forget that x prime is velocity. Now there's a different way you could think about it, though. Another way to think about this position differential is that it's a vector that points in the direction of the unit tangent vector and whose magnitude is, well, it's the length of the curve. Our linear estimate of the length of the curve. So ds. So that's another pretty reasonable way to think of the position differential as TDS. And what we're going to find is that in different circumstances, sometimes it's more convenient to think of dx as that. And in other circumstances, just because of whatever the particulars of that circumstance, it's going to be convenient to think of dx like that. So it's good to know both formulas. Okay. Okay, and then of course, what is ds? Well, ds, again, our linear estimate of arc length, and that's going to be the magnitude of that position differential. Okay. All right, easy to compute, of course, as speed times dt. Okay, so with all of that set up, and these are mostly just observations about, looking at a little piece of curve, how do I understand, what are the various aspects of that piece of curve and how do I understand them? How do you compute the total length from, starting at some point and then moving along a parametric curve and then ending at some point? How would I compute that? Well, I break it up into a bunch of little pieces, right? And add up the little bits of length. So really familiar concept, I hope. Each little bit of length, ds, just add up over the entire curve all of those little pieces of length, and it gives you the total length. Right? Y'all willing to buy that? Okay. Okie dokie. So there's your formula then, just an integral of speed, basically. And the kind of annoying thing is it sure would be nice if this was velocity instead of speed, but it isn't. It's important that it be speed, namely the magnitude of the velocity, right? If it was just velocity, you'd get displacement, which is not what we're interested in. We're not interested in finding that vector. That's not what we want. What we want is the distance traveled along the curve, which is ultimately why we have speed there. Okay, so why do I say this is unfortunate? Well, because speeds are magnitudes and magnitudes are square roots, and now we're doing, oh my gosh, we're doing integrals of square roots, and that's annoying, right? In fact, very often it's just not even tractable. So anyway, but nevertheless, that is how one would do it. Everybody with me? All right. So here's a related observation, and this is important for certain kinds of arguments that get made in certain contexts. that won't be Math 219. Nevertheless, it's an important idea, and you might see this in other contexts. So I want you to at least be exposed to the concept. So we're eventually going to work up to something called the arc length parameterization. The very first observation I want to make is to remind you that a curve can be parameterized in different ways. This, for example, is a parameterization of that curve. In fact, it's the, arguably the most convenient parameterization of that curve. It's the graph parameterization of that curve. So, easy one. But check it out. Weird though it may seem, this parameterizes the same curve. Because, you can explicitly see that this being my formula for x, then y has to be x squared, which it indeed is. You can see it right there. There it is, x squared. So y is x squared. Parameterization of that curve. So it's an awkward reality about parameterizations. They're not unique. There's lots of parameterizations for the same curve. Okay, and when there are two parameterizations of the same correction, when you are looking at two parameterizations of the same curve, you can relate the parameters themselves. In this case, it's pretty easy to see it. And you're like, okay, well, apparently t is equal to q cubed plus q. So, okay. All right. So another way to say this is that if you have a relationship between parameters, then you can turn one parameterization into a different parameterization, if you would have cause to do that, which we are in just a moment. Okay, so the big idea is to, instead of using time to parameterize a curve, what if we decided to use distance, right? We know how to compute distance. Got a formula there for how to compute distance along a curve. Distance, if I have a road, for example, like that, and I could drive along that road and say, I'm going to parameterize by my position as a function of time as I take that little road trip there. Right. But another perfectly reasonable way to parameterize would be to say, well, I'm going to define this to be where I am. This is s equals 0. And I'm going to say, if whatever point I might happen to be at later, the parameter that I'm going to associate to that point on the curve is just, well, what is this distance? So I'm going to redefine for this point and say, instead of the parameter being time that it took me to get there, I'm going to have the parameter be distance I had to drive to get there. Just a different parameter. And again, we can write down a relationship between the parameters, again, because we know how to compute arc length. So arc length, see, here it is, that distance s is an integral. It's an integral of speed. Specifically, an integral that starts at wherever point I'm calling my base point. That's where t is equal to 0, right? And then ending at at whatever time my initial parameterization, this time here, whatever time my initial parameterization gets me to that point. And so between those two values, I just, per the previous page, I integrate the speed, and that will give me that distance. Everybody with me? Yes.
Why are we using a different t?
Yes. Great question. That's the next thing I was going to say anyway. So he asked, what's the deal with this thing there? So first of all, I'll note that this is the lowercase Greek letter tau. In case that might be useful. Why do we have to use a different character? Why can't I just say x prime of t dt? And the reason why is because I've already decided t is going to represent, t is my parameter describing my location at the endpoint. And so t is fixed. T is one of the bounds for this integral, right? So I have to have a new variable that describes, that in some sense takes all the values between 0 and t. And it wouldn't make any sense to say let t start at 0 and end at t. You know what I'm saying? I mean, is t the endpoint or is t the thing that's taking values up to there? You can't have the same letter representing different things. So it's just, I mean, let me go back up, up to here and try to comfort you as follows. Do I really have to use t here? Is there anything magic about the letter t here? No, it's what we call a dummy variable, right? It's a placeholder. You know how when you do summations and you say sigma, I goes from 1 to n? Why do we call it I? Because it reminds us of the word index with so no good reason. You could use J or Q or whatever. So same deal here. This T is just, I don't know, arbitrary choice, whatever, doesn't matter. And likewise here, I'm using tau because here I really couldn't use T, but I claim that, again, having changed the dummy variable doesn't matter. Is that satisfying? Yeah, okay. Okie dokie, great question. Yeah, absolutely. Okay, so this is a relationship between S and T. You give me a T, I can compute the S. So what we call the arc length parameterization is what you get when you invert that relationship. In other words, solve for T as a function of S and plug that in for the T that was your initial parameter. And lo and behold, look what you get. You get position as a function of arc length. So altogether, this is called the arc length parameterization. All right, good news, bad news. The good news is there is something really nice about this. It's intrinsic to the curve, right? If I say, the parameter of at that point is whatever the distance is, it doesn't matter how I happen to drive along the road. I drive fast, somebody else drives slow, whatever, same amount of distance. So this business about being intrinsic to the curve is that's a nice observation. You might call it canonical. It's really the most natural. It's the most mathematically natural way to parameterize a curve. So that's kind of cool. Another nice thing, it's unit speed. So real easy observation. If position's a function of S and S is a function of T, then the chain rule tells us this. And take the magnitude of both sides. Of course, these are vectors, and that's a scalar. So when you take the magnitude of both sides, you get this. And in fact, if you think about it, both of these are the same. How do I know they're the same? Because they're both speed, right? This one says magnitude of the velocity vector. That's speed. This one says distance per unit time. That's also speed, right? And so those being the same thing, when we cancel them, we get the nice feature that that is 1, and therefore the derivative, using S as your parameter, the derivative, namely the velocity, as you use that parameterization, that velocity the speed is 1. So unit speed, nice fact. Okay, that's all the good news. Now let me give you the bad news. Practically inaccessible. If you have a parametric curve given to you and you want to find the arc length parameterization, oh my gosh, it's a bummer. Let me show you an example. And by the way, I don't want to say this is a best case scenario, but I'm aware of oh gosh, let me say how to say this. Practically, I cannot off the top of my head think of a non-trivial example that is workable. And what I mean by non-trivial, I'll make clear in a second. So let's walk through this example here. Here is a parametric curve, arbitrary parametric curve. It is not unit speed. That'd be easy to confirm. Computed velocity, not a unit vector. But how would I, follow the above process? How would I find, arc length as a function of time? Well, here's our formula. So let's write that down. How do we compute the derivative? Okay, that's no big deal, right? The derivative is easy. The magnitude is easy. Magnitudes are square root of a sum of the squares. So, no big deal there. A little bit of algebra to simplify it. And then let's notice, though, before we do so, this is a scary looking formula already. An integral of a square root. We've already kind of observed those are hard, generally speaking. It is only because I manufactured here a really convenient example, about the most convenient example I can think of that makes this thing under the radical actually turn into a perfect square. And of course, the square root of a square really simplifies nicely. So that was a slick move, right? That we got lucky there. Right? And so it's tempting to say, okay, it's all downhill from here because I've solved for s as a function of t. No big deal. There it is. And that's, we see daylight, right? It's all over. No, it's not. Because the next step in the process, of course, is to solve for t. And how would I solve for t in this equation? How would I solve for that t? I can't. It's cubic. I lose. Right? We lose. And so we're dead in the water on this. So even with the great pains that I went to manufacture an example where the integral of the square root, that whole problem worked itself out, I'm still just fresh out of luck when I get to the algebra at the end. So it's like I say, practically impossible to find an example that works. And so let me tell you now what I meant by trivial example. There are trivial examples that work. And what I mean by trivial is examples of parametric curves where the speed, this integrand turns out to be a constant. If it's a constant, then yeah, it's easy. Everything works out fine. But then again, if it's a constant, if the whole thing is silly and easy, right? So yeah, there's the trivial examples of constant curves that are already constant speed. Beyond that, they're all bad. Okay, so in practice, day in and day out, how much are y'all going to use arc length parameterizations? Yeah. It's not going to be a thing where you're going to be, first thing I want to do is take my parametric curve and convert it to an arc length parameterization. No, you're not going to do that at all. But there are observations that can be made, theorems that can be proved, that works out much better if you start by saying, I've got a curve and I get to parameterize it however I want. Let me assume the arc length parameterization. And then you can prove various facts. Okay, move it along. So vector fields. This is a new kind of a function. You've probably seen these in some sense or another before. Maybe not. If you haven't, don't worry about it. But a vector field is just a function from Rn to Rn. One way to think about it, just a function. But it's a function that we choose to view in a very specific way because in doing so, it allows us to model real world things that otherwise are extremely hard to model. So in particular, we're going to view the inputs as points, and we're going to view the outputs as vectors represented by arrows with their tails at that input point. That's how we're viewing it. And so let me y'all know me, and I'm a big believer in taking conscious recognition of what kind of picture are you looking at. These pictures down here are not graphs. They're not level sets. Let's see, what else are they not? They're not parameterizations. They are not literal representations. It's a new kind of picture. This is picture type number 5, therefore, for this course. So keep that in mind. Don't make the mistake of looking at, we're about to write down some formulas for some vector fields. And you're going to be tempted to, as usual, to think, oh, I guess the derivative is telling me the slope of something. Oh, no, not at all. That's graphs. This is not a graph. So the calculus of vector fields is a whole nother thing. Yeah, is that cool? Everybody see the warning there and what not to do, how not to think about these. Okay. Real quick, I'll entertain the question of, why would I be interested in these weird critters? And there's an easy example that I think kind of conjured by these two pictures themselves. These things, these vector fields, pictures that look like this and this, it looks like it's a really good model for representing how fluids flow, isn't it? Right? Otherwise, how would one represent fluids flowing around? You could have a fluid that, over here, the fluid is moving in that direction with maybe a certain velocity or what have you. But over here, different point, it's moving in a different direction, different velocity, different speed, perhaps. Right? So fluids move around in weird ways, and vector fields are a really nice way to represent them. So that's, I think the easiest, the most accessible answer to why would I care about these things is fluids work this way, and the world is full of fluids. Being, air being one of them, right? And so how air flows, big deal. How do airplanes fly? Right, that's a good question. Ultimately, it's because of fluid flows, and facts about fluid flows, which are understood by vector fields. Right, so it's really important stuff. Okay, so a couple of real, concrete examples. This first one, just kind of an easy sort of, example. This is a constant vector field, and notice that at every point x comma y, and keep in mind the input represents points. Right, at every point we have the same field vector. The value of the vector field, it's always the same vector, 2, 1. And so now keep in mind that it looks like I'm drawing a bunch of different vectors here. I'm not. I'm drawing the same vector over and over and over again at these different points. Right? Because so you could say I'm drawing different arrows, right? But they all represent the exact same vector. Okay, same direction, same magnitude, same vector. Yeah. Okie dokie. This next one is a little bit of a thinker. The input x comma y, keep in mind we think of the input as being a point. The output also x comma y. But keep in mind, we always think of the outputs as being vectors, which of course we represent with arrows. So in order to actually draw that, I'm going to reinterpret the input point. I'm going to reinterpret it as its position vector. That position vector is the same vector as the field vector. Keep in mind, again, the two arrows that I drew here, they're in different places, sure. But they point the same direction. They have the same magnitude as vectors. They are the same vector. So the position vector and the field vector are the same. Everybody with me? All right, and then so here I just kind of drew, what the vector field was doing at a single point. Now, if you kind of draw a bunch of those together, I think you could probably persuade yourself you get a picture that looks like this, because as the point moves, like if you move down here to a point there, well, then the position vector turns, and then the field vector, of course, turns also. Or you might say this, the thing to learn from this picture is that the field vector always points away from the origin, and the further you are away from the origin, the longer the field vector is, and that conjures this picture as well. Cool. All right. Here's another one. This is a pretty interesting vector field, as it turns out. And we're gonna see this one again later. Actually, come to think of it, both of these are actually pretty interesting vector field. This is a good one too. But that's foreshadowing. What's nice about this vector field with the position, thought of as a position vector, and the field vector being a quarter turn counterclockwise of that position vector, right? It is then not that, but a quarter turn counterclockwise. It's that vector. And again, play the same game. Think about what happens when you do a quarter turn counterclockwise of the position vector, every point, in space, and you can sort of see it effectively. It creates this kind of stirred pot kind of look. Does that make sense? Okay. All righty. Okay, this is a good one. This is important for physical reasons, or I should say physics reasons. This vector field right here, this is what we call a radial inverse square vector field. And a lot of people look at this and say, it's not inverse square, it's inverse cube. So what gives? Why do we call that inverse square? Because you can rewrite this formula like that and make the observation that what you have over here then is a unit vector. So one of the factors of magnitude in that denominator, one of them is actually just needed to kind of define the direction with a unit vector. And so what remains is inverse square. This unit vector, of course, always points radially, right? It is position. It's it's a normalized position vector, so it always points radially, and thus the term radial inverse square. Everybody happy? Yeah, question.
In this example with C being negative.
Yes, in this example, C is negative. That's right. And the reason I made C negative here, and that's why it's pointing inward instead of outward, so you're absolutely right, is because I wanted to make the connection to the examples I'm going to talk about here, in particular gravitational fields. Gravitational fields fit this form. And depending on the physics classes you may or may not have taken in the past, you may or may not have seen gravitational fields represented as vector fields. You may have just seen the gravitational acceleration represented as a scalar, right? But if you represent gravitational forces with vector fields, then this is the formula, and it is inward, of course, right? Thank God. Can you imagine if gravity were repulsive? There would be no planet, right? Whew, man, that was a lucky coincidence for the universe, wasn't it? Important little minus sign there. Okay. Side note, electric fields also take this form, and depending on whether you have a positive or negative particle, plus or a minus, what this constant is, a lot of details that aren't, our problem in a math class. But these are important vector fields, right? I mean, they're important forces, gravity, electricity, kind of a big deal. So this is an extremely important vector field to understand. We're going to do a ton of stuff with it later in the course, chapter 7, mostly chapter 7, as I recall. Okay. So let me in fact point out then that this actually gives us a completely different metaphor, a completely different way of thinking about vector fields, right? So the first observation I made was fluids. You could think of this vector field as representing, I like to think of it as a stirred pot, right? So yeah, it's a fluid flowing. Sure, that's a nice way to think about it. This represents a bomb exploded or something, right? And so, again, a fluid flowing. That's not what this is. Totally different metaphor. This is representing forces, not fluids. So something to be aware of, and I'll comment on this again in a few minutes, but something to be aware of is that both of these are really, really important. You can't pick one and decide I'm going to be a forces kind of person or I'm a fluids kind of person. Both of them are going to be really important, not just for applications. Both of them are going to be important for interpretations. In other words, developing an intuition for there's certain things that we're going to do. I have to be vague about that, but there's certain things that we're going to do that if you want to have any sense of why am I doing this and what is it for, one of them, yeah, you really need to understand vector fields from the point of view of forces. And another one of them, you really need to be able to think of vector fields from the point of view of fluids. So try to make a conscious effort now to develop, a comfort thinking about vector fields in each of those ways. Okay. All right, that's foreshadowing. Okay, gradients. Quick observation, we didn't really think about it at the time, but when we write down a gradient, it's a vector field. Again, we didn't think about it. They didn't have a need to think about it at the time, but if you take this function here, you write down its gradient, you write down a formula like this, and oh my God, look at that, it's a vector field. It's a vector that depends on position. It's a vector field. So that gives us a slightly new way to interpret a fact that we already know. Namely, we already know that, forget about this vector field business, we already know that gradients point uphill on graphs. Okay, so gradients point uphill on graphs, right? One of our first geometric interpretations about the gradient. So does that bear out in this example? I mean, not thought of as a single point, but thought of as a, vector field. Well, for this function here, here's the graph. I'm deliberately picking a familiar one because, the point here is not how to draw graphs. The point here is to make the connection that we're interested in. Anyway, there's the graph. What is the gradient? Okay, well, the gradient, there's the formula. We actually understand how to draw a picture of this vector field here. It's a lot like that x comma y vector field, but just twice as long. So this is really a lot like this one, right? Very, very similar, just longer. So it's this kind of radially outward kind of a thing. So it's hard to draw. And as observed, thought of as a vector field, the gradient always points uphill on the graph. And you can just see it right there. I mean, wherever you happen to be, this vector field is pointing uphill. Cool. So it turns out we'd seen gradients, we'd seen vector fields before, we hadn't even realized it. All right. Okay. All right, so a little bit of terminology. I'm going to start y'all off with my preferred terminology to try to recruit you into my camp. And then I'll confess the more common terminology in a minute. But here's a picture of a function where I take its gradient, which results in a vector field as we just observed. And there's no discussion about what to call this. It is the gradient. It's the gradient of little f. Of course it is. We've been calling it that forever. I would argue that it makes just as much sense to call this original function the antigradient of the vector field. And all I'm doing there is I'm borrowing, stealing, ripping off, whatever you want to call it, the whole terminology with derivative and antiderivative, right? Replace this gradient, replace that with just d by dx, and that's the derivative, that's the antiderivative, right? Of course, that's the extremely universal terminology. So I'm just recognizing that this is gradient, not just a regular single variable derivative, and thus the term antigradient. To me, this could not be more natural. This is so natural that if you were to actually say this to someone who had never heard that term before, but who knew what gradients were, you said anti-gradient, I'll bet you they'd figure out what you were talking about. It's right. Wow, could not be more natural. Okay, so that's my pitch. I hope you will join me in liking that point of view. But now let me confess that, yeah, in most contexts, people call it the potential function, which is not transparent, right? Is a potential function really weird? Why would we call it potential function? So the reason that it gets called the potential function is that having a function and taking its gradient to produce a vector field is a pretty big thing in physics. And it connects the idea of potential energy with the idea of a force. So there is such a thing as, I'm sure you all have heard, gravitational potential energy, which, okay, you probably heard it described as just potential energy. And it's higher up here and it's lower down here, right? That's potential energy. But that's actually gravitational potential energy. There's also electric potential and chemical potential. There's all sorts of, anyway. So potential energy, if you write down a formula for potential energy in terms of height, right? Take the gradient, you get a vector that points straight down, namely you get gravitational force, right? So potential energy and force are related by the gradient. The problem, well, one of the problems with this terminology though, is that there is a minus sign. And in fact, if you write down the formula for potential energy goes up as you go up. So the function is increasing as you go higher. So the gradient is actually upward, right? Which is awkward because gravity is downward. So oh gosh, so there's two ways that this can be handled. One is to say that the force is the negative of the gradient. Another option would be to have the potential energy be the negative of the anti-gradient. And putting the minus sign here is how things are typically done. And it's one of these circumstances where, since this is almost universally the case, I'm going to call this the right way to do it, just because, again, that's the way the world does it. So with this in mind, though, this thing, you can see kind of the argument for calling it the potential function, because it's the thing that connects to potential energy. And that's great. But then I like to point out, hey, quibble, this is actually an argument for saying that the anti-gradient is the negative of potential energy. This is actually kind of an argument against calling it a potential function because of that annoying minus sign. But anyway, that's my problem with it. I hope you see why I think that's super frustrating and suboptimal. But again, heads up, this is the language that tends to get used. So you're welcome to use either term that you like. I'm going to say anti-gradient almost exclusively. I've never said anti-gradient to anyone and had them, correction. I've never said anti-gradient to any mathematician and had them not know what I was talking about. Never happened. So I don't see the reason not to say anti-gradient. Be aware, though, however much you may or may not agree with that observation, people are outside of the context of this class mostly going to say potential function. And so, just be ready for that. And when they say potential function, I encourage you to think, oh, they mean anti-gradient. Okay, fine. Is that cool? Okay. All right. Okay, so let's go back to thinking about vector fields as representing fluids, or said differently, to think of fluids as the metaphor to understanding vector fields, right? So that point of view on vector fields. Lots of reasons why we might want to, right? I mean, what fluids might we want to understand the flows of? Well, air, right? Ocean currents. Pollution in any of a number of different contexts can be thought of as kind of flowing, right? Ditto atmospheric components. This is all three-dimensional fluids flowing around. There are some easy two-dimensional examples, animal migrations, right? You can imagine animals as being, it's kind of like a fluid, right? If you have a billion locusts. Right? They kind of call it a fluid. Some would say, well, yeah, but they aren't a fluid. And I would point out that, in fact, if you think about it, even fluids are a bunch of particles, right? I mean, that's their atoms, molecules. So, I mean, nothing's truly fluid. So I think it's perfectly reasonable to think of an animal migratory pattern as a flow of a fluid, but that's a flow of fluid that is two-dimensional. They flow along the surface of the earth. Right? Okay. Ditto surface water, how water flows on the, after it rains, the water starts flowing around. That's on the surface. Okay. Okay, so I want to do a little calculation here. This is a calculation that's going to be really important in chapter 7. And I want to recognize that I changed some of this stuff here at, was it about 9:50 this morning. Last minute, as I was preparing my lecture, I was like, you know what, here's a better way to write this. So this is a little different from what you have in your notes. I have not yet posted it to the resources section of the Sky site because, again, I was in a massive rush this morning. I was a little late getting here. So anyway, I just didn't have time yet. But anyway, so this will look a little different. It's perfectly equivalent to what is in the copy you have, and I'll have it onto the Sakai site, real soon. But anyway. So here's what I want to consider. Suppose we have a vector field and it's representing a fluid. In particular, though, it's representing the velocity of the fluid. So at any point, wherever you might happen to be, right, whatever that point is, the vector field, so the field vector at that point is the velocity of the fluid. Cool. Okay. Now I want to visualize a circumstance where there is a, let's see here. Well, I'll use yellow for this. This is good. Where there is a little piece of surface down here. A little piece of area. Reasonable question, if you have a fluid flowing and if you have a piece of area that the fluid is able to flow through, so maybe it's like a screen or maybe it's just an abstract piece of area that you're just visualizing. You could reasonably ask how much fluid's flowing through that area. Right? And just as a for example, easy to relate to example, imagine fishing with nets. Right? If you have a net sitting down there in the ocean, let's say, and the net is maybe hanging straight down, if it's just sitting there and if the water isn't moving, you're not going to catch any fish. Right? The fish will swim up and say, oh, weird, net, okay, all right, and they swim off. Right? So it's only if the current is flowing through the net, or maybe equivalently, the net is being pulled along behind a boat, that the net then will get the fish, or the fish will be dragged into the net, however you want to say it, right? So in particular, it's the flowing of the fluid through the surface that allows you to catch fish. And importantly, the fluid's got to go through the surface. Right? It's no good if you wouldn't catch many fish if you drag the net along behind you kind of parallel to your boat, right? Because then you'd be dragging that net and the fish would just be sitting there again, and the net would kind of go on by and the fish would be like, oh, it was weird, and then not get caught, because then they're not going through the net, they're going along the net. So specifically, it's the amount of fluid going through the net that would be interesting to understanding, how many fish you catch. And again, that's just, one example. For whatever it's worth, there's many much more important examples in physics that are not our job to talk about here, but I claim that there are lots and lots of examples. Yes.
So here, like capital F of X, is that the gradient?
No, there's no anti-gradient here. This is just a vector field representing a flow of a fluid. Yep, and so capital F is just a vector field. Yep. Yes.
How do we get to D dot N?
No, yeah. No, you're ahead of me. Yeah, I haven't gotten there yet. Yeah. Everybody with me so far, though? Okay. Okay. So, right. So I'm going to want to do a calculation here. As you see, we're going to want to calculate the amount of fluid passing through. It's going to be convenient to have this, this what we call a unit normal vector to the surface. That's this orange vector over here. And then I argue as follows, in some amount of time, delta T, you know, how much fluid passes through? Well, the amount of fluid is, it's this parallelogram's worth of fluid, right? I mean, that's given the way that the fluid is going and it's going through that area, given the shape that that area is, that amount of volume, you know, the volume of that parallelepiped is how much fluid flows through that surface in a given amount of time. Now, how am I going to compute this volume? Well, volume is height times area of the base. Yeah. What is height? Okay, now this is your question, I believe. Height, let's see here, there it is, height. I claim that that is the component of this vector D in the normal direction. Right, so that vector D, that's kind of, you know, that edge, if you will, of our parallelepiped. I can't just say, oh, how long is that? Because this parallelepiped is kind of tilted, right? But what I'm specifically interested in is to what extent does that D vector point in the perpendicular to the surface, thus giving me that height. Is that good?
Yeah.
Yeah, okay, yes.
What would D generally represent? Is that just one random
Yeah,
side of a parallel?
Yeah, it's any one of the four sort of vertices, you know, or edges in that direction of the. But yeah, what D is, we're going to get to in a second. Yeah, but for the moment, that parallelepiped has an edge there. Let's call it D, and we'll figure out what it is in a minute. Okay, so H is that component. How do we compute components? Of course, components are computed as dot products with unit vectors. Now, this is a flashback to chapter 1, right? Components are dot product with unit vectors, and N is a unit vector. And then, yeah, so what is the D vector? Well, let's not forget what's going on here. What's going on here is I've got a fluid that's flowing with a certain velocity, right? The vector field is representing the velocity. So basically, D is velocity times time. Right? The displacement, how much a particular little particle of fluid moved in some amount of time, delta T. Well, velocity times time gives me that displacement. So altogether then, what I've got is that the amount of, you know, the total amount of fluid here, which you know, oh gosh, I've used so many colors. I'm out of colors. This amount of fluid in here, right, is this expression. And if what you're interested in is how much fluid per unit time, well, you divide by delta T, and so the actual, you know, the more interesting quantity of fluid per unit time then is just this part of it, which is that F dot N times the area. And why this is interesting and what we can do with it, we'll pick up with next time. Oh, well, on Monday. So y'all have a great weekend, and see you later. Office hours in just a couple of minutes, of course.